According to the manufacturer of wiffle balls, they think that the ball will curve towards the wiffles. So if you throw the ball with the wiffles to the left, curve to the left. If you throw it straight, it'll go straight. If you throw it with the wiffles to the right, it'll curve to the right.
So first we decided to find the Reynolds number in our wind tunnel. Using the following Reynolds number formula, we could take the density of air, the viscosity constant of air, the free stream airspeed in the wind tunnel, and the diameter of the wiffle ball to calculate a Reynolds number, which is a way of differentiating different wind tunnel experiments. We found a Reynolds number of about 4,700, which is an order of magnitude less than what Professor Rossman found.
Because of the perforations of the wiffle ball, we're going to have asymmetry in the flow pattern in our flow field. We're going to have a turbulent boundary layer on the perforation side and a laminar flow boundary layer on the smooth side. And because of these two boundary layers, we see a difference in our point of separation with our flow across our wiffle ball. In the turbulent boundary layer, we're going to see our point of separation occurring further down in the stream, and we're going to see our point of separation in the laminar flow further up on the wiffle ball. And because of this, we're going to see asymmetry in our wake. We see this in our experiments in our wind tunnel, and we see our wake skewing upward towards the hemisphere where the smooth side is.
So from our free stream conditions, we found that there would be a high drag force up and to the right. We see that due to the asymmetry in the wake. And then from our streamlines, we find that there's a high pressure region near the top and a low pressure region near the bottom. And that results in a small lift force. And then overall, that'll lead to this ball curving up. And we see that the velocity is heading this way, so the ball will go this way and turn up.
Here are some images from Professor Rossman's research at Lafayette into the flow around wiffle balls. She was working at a much higher Reynolds number than us, and we can see that the flow is very different. For one, the flow flowing into the wiffle ball had a great effect on how it flies through the air, as well as the turbulent flow separates much earlier than the laminar flow.
So in comparing our results against what Professor Rossman found, in Professor Rossman's experiment, which was a high Reynolds number scenario, she found that the wake deflected downwards towards the side with the perforations. This would be consistent with a force downward, away from the wiffles. And her conclusion of why this occurred was that the wiffle ball was dominated by trapped vortices at this high Reynolds number. And that would result in the ball curving downward, which is consistent with what we see in the real world with a wiffle ball curving away from the side with the wiffles on it. Now in our findings, in a low Reynolds number scenario, we found that our wake was deflected upwards towards the smooth side. And our conclusion was that this was dominated by the boundary layers. We saw a turbulent layer across the wiffles and a smooth layer across the top. And this would cause a net wake upward on the side that's smooth and a net drag force upward on the side that's smooth. And this would result in our wiffle ball curving upward. Now this is not consistent with what we see in the actual world, but in talking to Professor Rossman, we found that the wiffle ball is dominated by trapped vortices at the higher speeds, and it switches to being dominated by the boundary layer conditions at our lower Reynolds number.
So another possible way our experiment differed from Professor Rossman's is the presence of edge effects. Because of the size of the diameter of the wiffle ball compared to the wind tunnel, it's possible edge effects might have been present. If we want to verify that edge effects are present or not, we can decrease the size of the diameter of the wiffle ball and increase the airspeed velocity in order to keep the Reynolds number constant. This would allow us to determine if edge effects were present. If our results were the same as with the normal wiffle ball, we can assume that the Reynolds number changing is what causes the flow to differ. However, if our results different from when the wiffle ball is a normal diameter, we can conclude that it's a result of edge effects.